Homework 4, number 4. Write a Raptor algorithm for a quarter-mile drag racing competition. Have your algorithm ask for the number of cars that will be racing. Then, for each car, ask the user for the quarter-mile time in seconds. Your algorithm will output the time of the fastest car, or the lowest time, followed by the number of cars that were within 1 second of that time. You may assume the time for at least one car will be entered. To design this algorithm, we first notice that we'll have two inputs. The first input is the number of cars that will be racing. And then the second input is the quarter-mile time in seconds. So we have two inputs. The first input is the number of cars. Second input are the times in seconds. And if we look more closely at that input, it turns out times, we're actually going to get multiple times. We're going to get one time for each car. So times will actually be an array value. And then we have several outputs. Our outputs are the time of the fastest car, and then the number of cars that were within 1 second of the fastest time. So again, our outputs are the fastest time, or the minimum value, and then the number of cars within 1 second of the fastest time. So looking at this algorithm, we could actually break it up into three parts. First of all, we have get inputs. That's step one. Step two would be output the fastest time. And step three is output times within 1 second of fastest time. This is specifically output the number of times within 1 second of the fastest time. Now that we've broken up our algorithm into three smaller parts, let's try putting this into Raptor. We'll add calls for each one of our smaller parts. So we've got 3 steps, 3 calls. First call, we'll call that get inputs. The second call, we'll call that output fastest time. And the third call is output num times within 1 second. So let's work on these steps one at a time. We'll start with get inputs. For get inputs, we're going to first ask the user for the number of cars as specified in the problem. We'll ask the user how many cars will be racing. And we'll store that result in num cars. Next, we're going to ask the user one at a time for the race time. We're going to use a loop for that. We don't want to forget our assignments for initialize and modify. So we're going to initialize and use I, and we're going to set that to 1. And then we're going to modify by setting I to I plus 1. And our exit condition is going to be when I is greater than the number of loops, or in this case, it's the number of cars. From here, each time we go through the loop, we simply want to ask the user for an input. So our evaluate step will be input the race time. What is the race time? and we'll store that value inside of an array that we'll call times. We can test this step to make sure that it's working. We won't get any outputs, but at least I can check to see if I get the proper number of inputs. So how many cars will be racing? I'll try 3, and then we'll use 12.21 as the race time, 12.75 as the next race time, 13.30 as the final race time. And we saw that the algorithm doesn't have any outputs, so we're not done yet, but it did take in 3 inputs when I said that I had 3 cars. We can also look at the values within the array, 12.2, 12.75, and 13.3, and we see that they match what we typed in. So we can see that not only are we getting 3 inputs, but we're also storing them correctly within our array. Knowing that our get input step is working correctly, we can move on to our next step of outputting the fastest time. Outputting the fastest time is simply going to be a loop. Remembering our assignments for initialize and modify, what we're going to do is we're going to loop through each value in the array, and we're going to store the values when we find the minimum. So we're going to set I to 1. We're going to modify by setting I to I plus 1. And our loop exit condition is going to be I greater than length of times. Now in order to find the minimum, we're going to want an additional variable that will be the minimum position. So we're going to set min position, we're going to set that to 1. This is essentially assuming that the minimum position is in the first position of the array. Now that's probably wrong, so we'll update that every time we go through the step, every time we go through the loop. So each time through the loop, our evaluate step is going to be look to see if the current position, or the position indicated by the index I, if the race time is in that position is smaller than what we think our fastest race time is so far. Here's how we do that. We're going to say times I, that's the current position, if times I is less than times min position, which is our current known fastest time. So if the current time is faster than our known fastest time, then we are going to update our min position. So our min position becomes I. In this way, every time we go through the loop, we update min position if the current time is faster than the previously fastest time. And finally, when we exit the loop, in order to output the lowest time, say output times at min position. We can test this step along with our previous step of getting inputs. We'll try 3 cars racing, 12.21, 12.75, and 13.3. So now it took 3 inputs and then it outputted the fastest time of 12.21. We're not done yet because we still need to output the number of cars that were within 1 second of the fastest time. But we see that both our get input function as well as our output fastest time function are working correctly. Ready to move on to our final step, output the number of times within 1 second. So we know that the fastest time is the time that's stored in times min position. So we're going to go through every value in the array and we're going to count the number of values that are within 1 second of times min position. So if we imagine we have all of our times, and they fit maybe in the range of high and low, this of course would be the value times min position. It would be the lowest one. And we're looking for all the values that are greater than that value but less than 1 second above it. So let's try that in Raptor with a loop. Remembering our assignments for initialize and modify, set I to 1, set I to I plus 1, And our exit condition is going to be I greater than length of times, and that will allow us to go through every value in the times array. And as we're stepping through, we want to compare the current value that we're looking at in the array to the one that we know is the smallest. So we have times I is times I less than times min position plus 1. And since we wanted all the values that were within, the number of cars that were within 1 second of that time, we actually want times I less than or equal to times min position plus 1. And if the answer is yes, then we want to count that value. So we're going to need another variable. We'll call this count low times. We're going to set that initially to 0. Because before we start, we have no cars that are within 1 second of the min time. And as we go through each one, if we find one that's close to the min time, we'll increase our counter by 1. And then finally, we'll want to output that value, count low times. So in this way, we initialize a count low times to 0, and then we start our loop. I is our loop index, which is initialized to 1, and we're going to go through the loop increasing I by 1 each time, and exiting when I is greater than the length of times. This will allow the loop to execute 1 time for every value in the array times. Each time through the loop, we want to compare the current value in times, whatever the value is at the index I. We want to see if it's less than times min position plus 1 second. If it is, we increase our counter variable by 1. If it's not, we do nothing to our counter variable, and then we check the next value, increasing I by 1. When we exit the loop, we want to output the count of low times. So we can test this using our sample inputs, 3, 12.21, 12.75, 13.3. We see that sure enough, we have the lowest time, and then we have the count of cars that were within 1 second of the lowest time. We can test other conditions, making sure that we have captured all the number of cars within 1 second of that time. To save some steps, we'll test against the server. And it looks like our algorithm passes all of these test cases.